But I believe that it's applicable for all of us. So basically, I've been working with Apache Spark recently. Apache Spark is the new kid on the block for data scientists, and so probably a lot of you have heard of Hadoop. So huge hype, and everybody had to use it, and so especially in big corporations, everybody had to have a Hadoop team. So basically, Hadoop takes this idea of MapReduce, which I'll slightly touch on, but it's a very intimidating environment. So if you just look at the names of all the pieces of software, there's Sqoop and Zookeeper. I think Zookeeper says it all, if you need a software called Zookeeper. So now it's actually been around a while, but I think Apache Spark is really taking off. It takes the MapReduce level, the MapReduce idea to the next level, and actually offers a unified solution. So you don't need 90 packages and Zookeeper. I'm not actually going to talk about Apache Spark. First of all, maybe my name is Johannes. I work at EMC as a mobile developer. But I've been a huge functional programming fan for the last 10 years in Haskell. So I'm going to introduce you to how Apache Spark takes a lot of ideas from functional programming that you can also apply in your own languages. And so we'll just go from there. So imagine if your application is effortlessly composable, testable, easy to reason about, and you can parallelize it and use it in a concurrent setting. Wouldn't that be amazing? I think probably for at least 90% of us here, that's not how we write software. So it's not composable, it's not testable, it's not easy to reason about, it's not parallelizable, and it's not easy to do concurrency. So the interesting thing is the solution has been around for a very long time. So there's some core ideas of functional programming that make all of those things achievable on some level. And I think these are some of the challenges that, we have been facing them, and many people have talked about them. So we have parallelism, which means that we have lots of data. We want to spread it out to multiple machines. They all do something, and then they come back with an answer. We have concurrency, and I think these two, they easily get mixed in together. In concurrency, you actually have multiple agents. So you have different things that happen at different times, and you need locking and synchronization and those kinds of things. And then the third one doesn't actually belong here, but it's just a side product. We have a challenge in having maintainable code. I think all of us have probably been in the situation where we start coding, empty screen, everybody's happy. 3 months later, big mess. How could this happen? So I think we have, as a profession, we have a bit more to do. And I think it has to do with this. So the state of the union is that pretty much every language we use is in one shape or another based on the C language. And so C was originally designed as a portable assembly. And for some reason, we stuck with it for 40 years. It's imperative, so we tell the machine exactly what to do, basically down to register level. We go take this from there, put it there, and so on. The whole idea of an assembly language is to manipulate global state, and there's a fixed sequence of steps. And so some languages that build on top of C, they've kind of weakened this idea about low-level abstractions, but basically everything is still a byte. In all the languages that we deal with, everything is a byte. And this whole model is not suited at all for distributed computing for several reasons. So just as an aside, the whole idea of abstractions, so modularity, can we build abstractions on top of abstractions? In C, we can't. Everything is a byte, and it stays a byte pretty much forever. So in a moment, I'll show you a sequence of 10 digits, and I'd like you to try and memorize them. So those are the digits. So how did you do? Do you remember all 10 of them? That's slightly out of order. That's correct. So there's this idea in psychology that we can handle 5 plus minus 2 cognitive units. So we can only juggle between 3 and 7 things at the same time. But what we can do is we can trick our brain by making the cognitive units larger. So if we say we have Christmas Day 2015, 6:30, then in a certain encoding, that's 15, 25, 12, 18, 30. That's something that we can remember a year from now. But the sequence of 10 digits, there's no abstraction in there. So we find it very difficult to deal with that. And I believe juggling the 10 digits is pretty much the equivalent of how we develop software. So we manage memory, we do loop counters, we do locking, and so we're so busy juggling all these things that somebody else could take care of that we find it hard to make sure that our program does the right thing, that it's architected well, and so on. And I think it kind of comes back to Brian Kernighan, who said, debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. And everything's somewhat fine if we're on a single machine with a single processor, with a single thread. We've kind of, over the last 40 years, we've learned how to do that reasonably well. Not very well, but we can kind of manage. But now we have quad-core processors, 16-core processors, the cloud, distributed programming, and or distributed computing, and this whole juggling completely breaks down. Whoever has written locks and synchronization by hand knows that it's absolutely not, it can't be done by hand, basically. And if you do it by hand and it works and something breaks, it's the worst place you want to be in. So I'd love if you just interrupt if there's any questions or comments or interjections, so just feel free. So a couple of weeks ago, Yannis talked about first-class functions and functional programming, and I thought there's a different side to the functional model. I don't really know if it has a name. It's usually lumped in with functional programming, and it's these three things. So it's pure functions, it's immutable data, and it's the idea of streams. And I think those three things, if we take them together, they kind of show a path of how we can do distributed computing in the future. So first off, what's a pure function? I was told I'm not allowed to show any Haskell code because it's going to scare people away. Luckily, ECMAScript 6 just came out, or it just was finalized. So I get to use a nice functional looking language that some of you may not have seen yet. But anyway, so this is that's a pseudocode / Haskell notation. It's a function from A to B. It takes an A and it returns a B. So it looks similar to what you've all been using, but it's a pure function. And being a pure function, it means it does not access global state. It has no side effects. So those two things, you go, yeah, we know all that. But actually, the function invocation can be substituted with the function body. So if I have a function and I call it somewhere, I can just take whatever the function body is, substitute it in, and be good. So that's something that you can only do with pure functions. And it can be used in an expression. So we have this, and I think I have it on a different slide. We have somebody 40 years ago decided to use the equals sign for assignment, and every mathematician has cringed ever since. So we have this confusion about equality and assignment. So if we, as computer scientists or programmers, we have no problem writing x equals x plus 1. Mathematicians are a bit confused by that. So the pure function can be used in an expression, which means that we can build expressions from pure functions, and that's how we actually grow and put things together. We can do things like memoization. So because it's pure, it has no side effects, whenever you give it the same A, it will always give you the same B, which means you can have a little memory, can attach a little memory to it, and whenever it sees an input it already did, it can just return the output it already had. Oh, sorry, that's a typo. And it's idempotent. So the idea of idempotency is that you can execute or you can evaluate it multiple times, and it will always come up with the same answer and have no adverse side effects. So if you take any function in probably your source code, they wouldn't be idempotent because they deal with state, and so they would manipulate stuff. There's a counter that gets increased or something like that. So a little overview of pure. So the opposite of pure is impure, but that sounds a bit mean. So the opposite is effects. So on the pure side, we have stateless. There's no sequence because there's no state. And when there's no state, there's no time. So everything is just a big expression. You're just building big expressions where you don't have to track. So x was 1, and then I increased it, and then I checked what it was, and then I increased y. So I don't know if you've built those tables at some point in the past trying to debug things. It gets really fun. And then what I already mentioned, so in pure functional programming, x equals 1 plus 4 is actually equality, whereas in the languages we know, x gets assigned x plus 1 is actually something completely different. So here again, we can, wherever we find an x, we can just substitute the expression, whereas here we have a changeable memory slot. So those are completely different things. So the fancy term for this is referential transparency. So if at any other point I calculate 1 plus 4 and I calculate 1 plus 4 here, well, that's actually a bad example. But if I have two of these expressions, I can just calculate them once and use them again. Again, idempotent, and yeah. So pure functions, that they're not very useful in themselves. We want to interact with the real world. We want to interact with storage, the network, very importantly, the screen, the keyboard. So for all of those things, we need to access global state and have side effects. So what we need is both pure functions and controlled or contained effects. Let me just see if I'll just skip one slide. So what we're looking for, and this is kind of a Haskell notation, is we want to write pure functions that are doing their own thing. Whenever you give them the same input, they return the same output. But we also want to embed them in something that does something useful. So here the blue thing is effect land. So here we can access memory and we can access the screen and the network. But we have this shielded portion of pure function that is completely stateless. And we have some kind of mechanism. One of those mechanisms is Apache Spark that manages this for us. So it will connect these pure islands in some sensible way with each other. And if we try to maximize the white area and minimize the blue, we still have a program that we can reason really well about. So as an example, we have some kind of value a that comes in, a function that goes from a to b. Then we have a stateful value b, go from b to c. They both can go into here. So obviously, as the graph shows, it's very simplified. But here we can do I/O operations. We can do network and all of those things. And then the other thing, immutable state. So we're all very used to changing state. Object-oriented programming is basically all about mutating state. So the idea of immutable state is you have a list, you append a value, and you get a new list back. But the original list is still there. So, and there's some nice properties. This is inherently thread safe because the old list stays where it was, your new list is your new list, so there's no thread contention. You can share as much as you want, internals, everything, because you will always, whenever you change it, you just create a copy that it reflects the change. And everything is atomic, because everybody, every function, every method, everything operate on their own piece of data, there's no overlap between that. So Haskell and a couple of other languages, they have some nice features that you actually share the data so that it doesn't explode in the heap and all of that. But just as a general principle, immutable state is making a great comeback. If you look at the actor model, Akka, some things that Java is doing, basically everything that's new and shiny will ask you to do immutable state. So Java Spring, they are very encouraging of immutable, or even enforcing of immutable state. So this idea of going to a memory location, tweaking it, really makes it hard to reason about, impossible to distribute, and just it's a problematic idea, hard to build modular things out of. And then the third thing on the list that I showed you is this idea of streams. And depending on the language that you've used, you may have come across terms like generators or iterators. Not quite the same thing, but the same idea. So we have a list here, and that's JavaScript. We have a list here, and we say, I want to map over the list, and for every value, I want to add one, and it will return a new list. So it will return the list 2, 3, 4. And then on the right here, we have how we usually write this. Sorry, that should say access.length. But so we have a list, we say we have a result array, we iterate over XS, and we say append to the result the value of XS at location I plus 1, and then return the result. It seems crazy that we're still doing that, but we are. So which do you think is easier to parallelize? If I want to do half here and half there, the compiler would have a pretty hard time understanding what you're trying to do, figuring out how to split the list in two and reassembling it and all of those things. Whereas here, you're using an abstraction and you're using a very declarative syntax. So you say, go over all the items, increment them by 1, done. So here, there could be implicit sequence. So you say, first you have to do the first element, and then you have to do the second element. And because this can have side effects, you could actually be depending on the sequence. So basically, the compiler can't do anything. Whereas here, because of using a lambda expression and a couple of language features, you tell the compiler, I don't care about sequence and ordering and all of those things. Just make sure that you've applied this pure function to every element and give me back the result. So the compiler can decide, hey, I'll send this the first half of the list here and the second half there, and that's fine. So it's really the idea of using good abstractions and also the power of pure functions that comes in here. One thing that's really cool with streams, and that gets implemented in a couple of languages, I think Java 8, they're working on it, Haskell has had it for a while, is this idea of stream fusion. So if those things here, if they're side effect free, you have all kinds of possibilities to optimize your graph or your chain, and that's again exactly what Apache Spark does. In Apache Spark, you build a tree of calls and maps and all of those things, and then you have an optimizer, very much like in a SQL database, that goes, let me look at what you're trying to do. Oh, I'll just reshuffle these things here, and look, it runs 10 times faster. So basic idea, stream fusion, I have a list, I map x plus 1 over it, and I map times 2 over it, and then the compiler goes, oh, let me fix that for you. And it turns it into one map, which first does a plus 1, and then it times 2, and now you're only touching the elements of the list once instead of twice. Very trivial example, but if you're building really big chains, really big trees, there's huge performance possibilities. For example, if you write a filter behind here, the compiler goes, oh, let me put the filter in front of it, do the reverse of this, and then I filter first, and then I don't even have to apply the function in the first place, or only to a very small subset. So if and only if the functions we're using are pure, the compiler can combine those map and fold and filter operations that Yannis talked about, the compiler can reorder and optimize the entire chain. And if you're using laziness, as Apache Spark does, then we can actually optimize across functions and locations. So I'm doing a map here, returning the result, or the reference to that, doing a map here, and if I don't actually evaluate that but leave it lazy until it's actually needed, I can do the optimization on a global level. So I hope I'm not rambling away. So any questions so far or comments?
Creation of pure functions.
Say that again?
Creation of pure functions.
Yes.
I mean, would like the list of pure functions just increase linearly almost as you go on?
So what's the question?
Would the number of pure functions you're generating increase? Like, I mean, you have to continuously define new pure functions.
Yeah, there's an infinite number of pure functions, possible pure functions.
So I mean, like, isn't that like kind of taking away from the time saving? I get the whole optimization, evaluation.
Yeah.
But I mean, you have to define a new pure function for each particular instance of the problem you're trying to solve, don't you?
Yeah, you define pure functions. Yeah, a lot of them, hundreds, thousands. But they're not different from the functions or methods that you would have been writing. They're just constrained in that they're not allowed to have side effects. So I don't know what environment you work in, but you probably write hundreds of thousands of functions or methods. So they're exactly the same. And so language support there's very little language support at this stage. So Apache Spark, they've done it in the form of a library, and then probably, but languages don't really have this concept yet. But I very much assume in the next, within the next 5 years, we'll see those kinds of constraints coming up. So as I said, Java Spring already, all the interesting objects that Java Spring as a framework uses, they're all immutable and guaranteed to be immutable. Does that kind of make sense?
I get the idea.
Okay.
Do you have an example of how the...
After what?
Transition from the effects to the actual pure functions?
That's magic. So that's something that the compiler, ideally the compiler or the framework would do for you. So it gets very, I don't know very much about it, but it gets very algebraic and so you have to prove that you're doing it correctly, because otherwise everything goes up in smoke. So the people who write Java Spring and who write the Haskell compiler, they would spend quite a bit of time making sure that how they do the plumbing, that is correct. But basically, it's I don't know. Maybe I can come back to that in a moment. So Apache Spark. So the idea of the author was to express the structure of workloads in terms of abstract algebra. Sounds incredibly unsexy, but basically comes back to what I just said. You want to. So with MapReduce, what you have is you have a data source. You fan it out to machines, they do something, you reduce it back, and then you have your result. So it's very linear. And the idea with, so whenever you want to do something where you need iterations, so a lot of the data science algorithms, they need iterations. What Hadoop actually does is it reads from disk, does something, writes to disk, comes back, goes, oh, I need to read from disk, reads from disk, does something, writes to disk. If you do that thousands of times over a Hadoop file system, that's not great performance. So the idea of Spark was, let's have like a SQL database. Let's have an optimizer. We have a declarative language similar to SQL where we describe what we want, and then the optimizer goes off and ensures that the number of disk accesses are minimal, that everything is cached, that when one node has touched data before, that same data comes back to that node again. So it's a tree optimization thing. So coming back to what I said before, we have two things. We have pure functions and effects. Spark calls them transformations and actions, but it's really the same thing. The transformations, they're lazy, so you get to build them up. And only when you want the result, you actually evaluate the whole tree. you can create an arbitrary operator graph. So you can say, I want to map, and I want to filter, and then I want to do this. And so you can build, I'll show you a picture of a graph. And so these functions that Spark is using, we should write them as pure and as idempotent. So Spark can go, oh, that node is taking too long, same as Hadoop. I'm going to kill that node, start that part of the job again. So we can't have side effects. We can't, those, in the transformations, we can only do pure functions, and Apache Spark actually ensures, so this, by the way it sets up the environment, you can't actually have side effects. And then you have actions, and what they do is they take this graph that you've been building out of transformations and collapse it into a value. So that's whenever you call an action, that's when the optimizer kicks in and says, oh, let me have a look what you're trying to do. Let me see how many nodes I have available. Let me map it out, optimize it. And so they have this idea of the resilient distributed data set, RDD. So that's their data type. So that's what they hand around to build up this tree. So whenever you have a transformation, you grow this RDD and you make a chain or a tree out of it. And I know that has all been a bit dry. So let me see. No, actually, let's start here. So this is a very short example. It's the word count, which is kind of the hello world of the machine learning or data science community. So basically what you say is, I have some text file that could come from your local machine. Probably if you're using Spark, you have big data to work on. And you say, I have a text file, please read it in, and it will already turn it into lines. So then you have like millions and millions of lines. And then you say, so this is Python code. Then you say, for each line, I want to split it. So it splits it at the tokenization, it splits it at white space. And the flat map turns this list of lines, list of words into one big list of words. That's what flat map does. Then you say, for each of those words that I just created, I want to create a tuple, word and one. And then I say, go over this list of tuples and reduce it by the key. So it looks for every word that is the same. So it looks for all the words, word 1 here, word 2 here, and it adds up all these ones. So that's how it counts words. It's a bit of a roundabout way. And then it comes back with the answer and says, this word occurred 20 times, this word occurred 900,000 times. And so the flat map and the map, those are your transformations. They're lazy. You just tell Spark, I want to do something to these lines, and then I want to do something to the result of those lines, and then this reduced by key is actually the action, which then forces the tree to collapse. It sends it out to the nodes, they do their thing, and then it comes back as the answer. So what this actually looks like is it gets turned into a tree. I don't think it's for the same code, but it's the same general idea. So we have one original data set here, one data set here. We fan it out to, we group it in this case, group by. This one, we just do a map. So every element gets transformed in some way. We do a filter, so we only use a subset of those, and then there's a join. So this is what those trees look like in Apache Spark. So all of that, what you see here is you've defined lazily, and then you hand over that tree to Apache Spark, and it will optimize it for whatever distributed architect, or however many nodes and what they look like. So the key takeaways from my perspective are parallelism and concurrency. They're here to stay. And I think the languages that we're using, they are inadequate to deal with it. So if you have Java, but if you have C++ and Python with their global lock, and so basically most of the languages that we use, they're not well suited for So what I showed here was parallel programming, so Apache parallel computing. So Apache Spark takes one big set of data, fans it out, does something with it, iterates and so on, and then comes back. But the same also applies to concurrent programming. So if you look at Akka, for example, which is a library for the actor model for Java and Scala, they also, or if you look at Erlang, they also have this idea of pure functions versus effects. They have this idea of immutable data, and they have the idea of streams, so that you have some kind of collection that you can filter, map, fold, what Yannis talked about. And I know your language very likely doesn't have support for these things, but I think it's also, I like the title of this YouTube channel, Mental Floss. So it's also something how we can keep ourselves sane. So I remember a long time ago, 15 years ago, I was writing C++ code and trying to optimize and pointers and references and, oh, I can make this even faster, but it never worked. It was always wrong. And then one day I decided to just copy everything, don't reuse it, just always copy, and use immutable data, try to keep your functions as pure as you can, and all of a sudden all the complexity went away. It got a little bit slower, but I was able to really build the complexity up, which I wasn't before, because I couldn't even implement this most simple algorithm in a way that was correct. So yeah, contain your state and effects as much as possible. So even if your language doesn't support pure functions and immutable state, you can still get a long way. So in C, you can use const, Java, you can use final, and so on and so on, and work with it that way. So I know it was a little bit, or I think it was a little bit confusing parts of it, so I'm happy to take questions to minimize that confusion as much as possible.
So you were talking about the possibility of Spark or that system handling what happens with memory, because immutable state is great, but what happens then when you're talking about massive volumes of data and you're doing these complex operations and recreating, copying, creating copies or whatever. So
Yeah.
I know you're talking about distributed computing, so it's going to be on lots of different machines and maybe all thrown individual resources, but are you going to run into an issue there, like depending on complexity of the data sets and the complexity of the actions that you're taking on them?
Not in the context of Spark, because every node should only see the data they need to do what they do. So they need to look at that data anyway. So that's part of the optimization piece, that let's say you have 10 gigabytes, 10 terabytes of data, and you have 1,000 nodes, then you may not be able to do everything at once. So then you do one part, the first half of the data, let that compute, and then you do the second half. But you don't really, the same as with SQL. Like SQL probably does amazing things in the background that most of us have no idea, what they're doing. They're changing these joins and turning it around and inverting it inside out, but we don't care. We just say, can you give me a join? And then it goes off and does its thing. So it's really the same idea, but in a more general computing sense.
Yeah.
So in general, if you copy everything, all the data, all the time, you will run out of space. And that's one of the issues that Haskell has. But then the goal is to make your compiler smarter and do more sharing, more copy on write, and those kinds of things.
Is that kind of thing appearing in those compilers then?
In Haskell it is, so it's still got huge heap consumption, but it's very performant. So maybe we don't even care. Like it spawns up stuff and then destroys it at an insane rate, but it's very fast doing it. So in other languages, I see the trend very much going this way, that we get. So immutable is already here. So if you look at some of the cool frameworks that are out there, as I said, Spring, Akka, and so on, they already use immutable state because it's the only sane way, or the only way of doing distributed stuff. And pure functions, I don't know, I haven't looked at Java 9, what they're coming up with, but I assume that sooner or later they will support that in one way or another.
Is there any fundamental reason why JavaScript or C-type languages can't have pure functions or have this kind of functional stuff? Like it is a lot more than syntax, obviously.
Yes, that there is. It's hard. So one thing that you run into immediately in Haskell is you go, oh, I've got these lovely pure functions. Let me just, I just want to do a system print line or a console log. And you go, side effect, can't do that. So it takes a completely different approach to everything. Like it's, C did its thing well. It's a portable assembly. It's done great job. But it's very, you go, oh, I'll go to this memory location and I increase it, and then I go here. So we like, I really can recommend looking into Haskell. It hurt my brain for a long time because it completely, everything is different. But you get a lot of things for free then. So a lot of things, so basically everything that's easy now gets hard, but everything that's impossible now gets possible. So concurrency is amazing in Haskell and similar languages. Parallelism and so on. So no, you can't. There's no way you can just retrofit it. You have to change the entire approach. But basically, that's what's happening. So if you look at Java 5, 6, 7, 8, they're very clearly moving in that direction.
Do you have any thoughts about Clojure as a language compared to Haskell? It's a functional language, but it still has some side effects. Sort of stuff.
Yeah. I don't know. It's a hard question. I haven't done much Clojure. I don't think there's a silver bullet out there. I'd be kind of hard pressed to write like a huge enterprise application in Haskell because there's still some corner cases that are still kind of tricky because when you do pure, so basically you can either do completely pure with contained effects or not. But I don't know, to my knowledge, Haskell is one of the very few languages that do completely pure. And as soon as you allow a single side effect, all of these things, stream fusion and optimization, they all go out the window because your compiler can't assure correctness anymore. As soon as you allow side effects, then you lose pretty much all of the benefits.
You were talking about lazy application.
Yeah.
Is that the analog of lazy evaluation in Haskell?
I don't know, what did I say?
I don't know, it was on this slide, lazy application, but
okay. No, it's the same concept. So, but you have that in other languages as well. So in JavaScript you have futures, in Java you have promises. So every language comes up with it in one way or another. So, but the idea is that you can, but I guess you're very aware, but I guess, so the idea is that you can chain up things and keep them chained instead of evaluating them in the middle. And then you can do global optimizations on that. So you can say, oh, this one, I've seen that over there, and they're exactly the same, so I'll only evaluate them once. And because of referential transparency, because they're the same expression, they will have the same value, or evaluate to the same value. So sorry if I used the wrong term there.
So, in your opinion, is the main use case for functional programming distributed big data uses? Or is there a reason to look at it for like single-threaded applications or even single-machine applications?
So short of verification, so if you write an operating system and you want to verify that it does what you want it to do and doesn't have any backdoors and side doors, short of that, you can do pretty much everything in your language of choice, C, Python, Ruby, and so on. So I think functional languages are great. I think they're more modular, more composable, easier to reason about. But the upside is limited because we've learned to work around our crappy languages. But distributed computing you can't. Parallel computing you probably still can, but concurrent programming, I think you can't really write at scale. Like if you do locks and semaphores and synchronization, like 20 lines in, you already have an impossible to debug mess. So how are you going to write like insanely huge applications? So one way that
It's worth it to even look at it.
Yeah, definitely. Yeah.
Distributed nature of it.
So I think we're kind of slowly coming around to it from really weird angles. So now everybody talks about microservices and RESTful APIs. Well, RESTful APIs are stateless. So we're doing functional programming over hypertext protocol. So like we found a really roundabout way of doing that. But yeah, it's definitely very worth looking into.
Just wanted to add a comment to that. I come mainly from a functional background, so I may be a bit biased, but just the testability of your program increases when you do functional, because you build functions that you can compose together like Lego blocks, and you build your castle. And you can test each of those functions individually. You can say, you have libraries and stuff like quick check, and you can say, this function has this property, and then you can tell the library, just throw inputs at that and make sure that the function actually does what it. So you can build your test suite, and it becomes your specification. So just in terms of testability alone, you win a lot when you write the function.
Yeah, I can see that. Just unit tests alone for pure functions would be 1,000,000 times easier than what I do.
Like it often is the case that your pure function is actually 60 characters long. So it's not only does it fit on the screen, but it fits on like 2 lines. So you can actually look at it and go, map, filter, fold, and there's not a lot that you can do, unless you have a very systemic problem where you're just doing the wrong thing. But you can't, it's very hard to do off by 1, or I computed the length of the list, instead of whether it's I++ or ++I, those kinds of things, they all go away because you look at it and you go, yeah, it looks about right. So yeah, I completely agree with that. I just think we've learned to build large applications in imperative languages. So there's still the gap isn't so big there. Okay. Cool. Thank you very much.